Okay, in this video we are going to talk about the deletion, but there's just a small unfinished discussion about the minimum. And we have already talked about minimum. To get a minimum of a BST, we want to start from the root, go left, and go left. And when there's no left subtree to go, we stop there, and that is the minimum, right? And then, well, what is the running time? Well, is that O log n? Or we should say this is theta height, right? So theta h. Okay, and then what else? Well, we still have to consider whether it is a good BST, a balanced BST or not. So, well, if we are lucky, we have a super balanced BST, and then it could be a O log n. And then if you're unlucky, it could be O n. Okay, so that's the running time of the minimum. Okay, and the next thing, well, we also have to do the deletion. We want to have a successor, and for the successor, the definition is if we have a node, the successor of this node is the node we are gonna visit next when we are doing in other tree block. Okay, let me repeat that. Well, if you have a node, the successor of this node will be the value or the node you visit next after you have touched the current node when you are running in other tree block. Okay, so using this idea, and what is the successor of node 3? So node 3. So after you finish visiting the 3, and then what is the next node you are going to visit? That will be 4. Why? Because after we visit 3, and then we are going to visit the right subtree of the 3, and then the first node and the only node we have on the right subtree of 3 will be 4. Okay, and then how about the successor of node 15? For the node 15, after we have finished visiting 15, the next and then we will go to the right subtree, and on the right subtree we will go to the left side, and then we will visit 17. So 17 is the successor of 15. And how about 13? That is really hard. So after 13, and we will find there's no right child to do, and then this means we have finished the subtree of the 13 and 19. And then have we finished 7 already? Yes, because we finished the 17 and we finished the 7, and then we will move down to the 13 and 9. And then how about 8? Sorry, how about 6? 6 is already finished. Then we can go to the right side. And then after 13, there's nothing to do on this part, so we will visit 15. So 15 will be the successor of 13. Okay? And then what are the general rules for finding the successor of the node x? So there are really two cases. The number one, if x has a right subtree, and then you want to go to the right subtree, you want to find the smallest value on the right subtree, and that is the successor of x. Okay, so the case 1 is easy. But for the case 2, if x has no right subtree, and then the successor of this node will be the first ancestor of x, and whose left child is also ancestor of x. Okay, it sounds hard. Okay, so let's say if we have the 13, we want to go up and find the ancestors of 13, and we want to find an ancestor of 13 whose left child is also ancestor of 13. So if we go up, we have 7, and then 7 doesn't really have a left child, and then we go to 6. 6 has a left child, but the left child of the 6 will be 3, and 3 is not an ancestor of 13. So we go to 15, and then for the 15, it is an ancestor of 13, and the left child, which is 6, is also an ancestor of 13. So 15 is the successor of 13. Okay, so this is how we can find the ancestor, the successor. And then if you want to find a predecessor, so the definition of the predecessor is just the opposite. A predecessor of a node is the node you visit before using in-order tree walk, before you visit the node of X. Okay, so it's just the opposite of the successor. Okay, and after talking about the predecessor and the successor, now is the time we want to talk about deletion. And deletion is really tricky. Okay, there are three different cases. And the case one, if X has no children, the easiest, right? So if X has no children, we just throw this node away, and then we are not breaking anything. So case one, really easy. And for the case two, if X has only one child, okay, what should we do? The only child is going to take the position of the X, the node to be deleted, and then that's it. Okay, that's case two. And for the case three, that's really the hard one. If X has two children, and then you want to find the successor of X, you want to swap the X with the successor, and then the successor will stay at the X position, and then you move down and you figure out a recursive way to delete the new X. Okay, and then at the new location it will be either a case 1 or case 2. Okay, really tough. So let me show you some of the examples and say, how do you want to delete K? So deleting K, which case is that? That's case 1, right? Because K is a leaf, so there's no children. How do you delete K? Grab the K, throw that away, that's it. Okay, and then how do you delete H? So to delete H, this process is called splice out. This means we are throwing H away, but we want to connect H's parent to H's only child. So F will refer to K as the rare child, and then that's it. Okay, so because H has only one child, and the only child will take the position of H. Okay, and how about B? If we want to delete B, which case is that? Case 3, because B has both of the children. And the next question, what is the successor of B? So how do you define the successor? The successor is you want to go to the right side, and then on the right subtree you want to find the minimum. And what is that? That is C, right? So how do we do the change? We want to swap the B and the C. So C will, let me write down here a little bit. So C, oh no, what's going on? Okay. Oh, that's so annoying. Okay, so let me grab this. Let me paint it here. And then we are gonna have C here and B here, because those two are gonna swap the location, right? And then, well, C, the successor, will take the B's location, and then we are gonna delete B at the new location. And then after we have swapped the successor with the value to be deleted, and at the new location of the value to be deleted here, and it will be either case 1 or case 2. In this case, it will be case 1. So this means we can safely delete the B, and then the C, the successor, will take the location of the B, and this is how we can delete the B. Okay, so let's see another example. And well, for this tree, we are using the values, and how do we delete the key 3? So for the 3, when we are deleting that, which case is that? It is case 3, because 3 has both children. And then if 3 has both children, and then what's the rule? We find the successor. We want to swap the 3 with the successor, right? So for this tree structure, what is the successor? What is the successor of 3? and the 3 will be swapped with the successor, and the successor's value is 4. So we are going to swap the 4 and 3. Okay, and then we want to delete the 3 at the new location. And then to delete the 3, this is a leave, so this is case 1, so it will be deleted. And then 4 will take the location of 3. So this is how we can delete the 3. Okay, so let's go back. And the next thing is, how do we want to delete 7? Okay, so let's come back. How do we want to delete 7? To delete 7, which case is that? That is case 2, because 7 has only one child, and then we are going through the process called splice out. This means we want to connect 7's parent directly to the only child of 7. So now 6 will have 13 as the direct right child, and then 7 is going to be thrown away. So this is the case 2. We delete 7. Okay, and then let's go and see, how do we delete 6? Okay, that's interesting. To delete 6, well, 6 has 2 children, so that is case 3. Okay, and then how do we find the successor of 6? We want to go to the right subtree. On the right subtree, we want to find the minimum. What is the minimum? The minimum is 7, right? So we want to swap 6 with the successor. So 7 goes here, and then 6 goes here. And then after that, we want to delete 6 at the new location. And then how do we delete 6 at the new location? Or I should ask, which case is that? Now at the new location, 6 has only one child. This brings us to case 2. And then to do the case 2, we want to do a splice out, right? So we want to get rid of the 6, and then we directly connect the 6 parent to the only child of 6. So 6 is gonna thrown away, and then for the 7, it will have the right child to be 13. Okay, so this is how do we do those 3 deletions. And then let's continue our discussion. Well, we do want to ask why, after we have done one step of case 2, and we will either go to the case 1 or case 0. So when we start from the case 2, and then we want to go to the right subtree, and then we want to find a successor. And then when we find the successor, and it will guarantee one thing. If that is the successor, that is the smallest value on the right subtree. It can have right subtree, but it cannot have left subtree. So this will guarantee that after doing the case 2 for once, we will go to either case 0 or case 1. Okay, and then another question is, just now we also talk about the predecessor. And can we do the swap the x with the predecessor instead of the successor when we are doing the case 3? And the answer is, actually it is possible, and this algorithm is still correct. Well, if you want to do that, and you won't really break anything. Okay, so this is the end of today, and for today, you do want to continue read the section 12.3 at this book, and the next lecture we will talk about how can we make a binary search tree balanced. Okay, we do want to have balanced binary search tree instead of super unbalanced ones, and then we can have faster searches. Okay, so I will see you in the next lecture. Bye bye.